So, our fifth meeting here. It's about computational models in architecture. And last time we started discussing these early connections between computers and architecture. And these connections between them were mostly on the level of infrastructure, not on the level of design, if you remember. So I introduced you with this idea of what is a polynomial and how polynomials became one of the mathematical bases of geometric modeling. And because of that, how they became kind of base of the infrastructure of modeling in computer-aided design. And we demonstrated how Bézier in the 50s reverse engineered this Bernstein's method for polynomial function approximation and created a method that allows you to actually create a curve by specifying its control points. So reverse engineer the whole thing, not from a function towards a polynomial, but from points towards the curve. And then this extended into surfaces that could be also specified by a set of points, and this set of points was called control polygon or control cage. Then I showed you what kind of geometric modeling came about from this infrastructure. We talked about 2D CAD modeling, 2D CAD drawing, 3D wireframe modeling with lines. Then we went to polygonal modeling, which is modeling the surface of an object with kind of flat faces. And then because these flat faces are kind of rugged, if you want to have it smooth, you need to subdivide them. Then we talked about solid modeling, and the idea is that you can distinguish between what is inside, what is exterior, what is interior, what is the boundary. And then we talked how this actually is important if you want to make simulations. And then finally, I showed you how this field of computer graphics relies on all of these methods in order to kind of create a perfect simulation of a real world on our screens, or for that fact, an imaginary world, looking world in front of our screens. And as architects, of course, you are already familiar with these things, or at least you're exposed to them. So even if you do not know exactly what is their history and how they work, you still kind of have an idea of what this is about. And today, I want to show you another perspective to modeling with computers, which is more kind of research-driven perspective. And I call these kind of models computational models in architecture. And why I call these models computational, when clearly all the models we have already seen also depend on computers. So why is this special? So difference here is that these models I'm about to show you, the modeling process itself relies on computational procedures. So in computer-aided modeling, so CAAD, this computation happens behind the scene. So you work in geometry, something happens behind the scene, and you get geometry as a result. And this modeling is, because of that, pre-specified, pre-programmed in the infrastructure. So you simply use the software. And these computational models, you actually model objects by writing code. And then to render it into geometry, you, of course, at the end use the same infrastructure as these old methods. So at the end, you need to have a rendering, you need to have lines, you need to have surfaces. So you render them back to these old style infrastructures, but you model with code. And if you remember this slide, this was 2 lectures ago, and I was talking about origins of computation. So remember the title of Turing's paper, which introduced computing, was actually a response to this Hilbert's question about Entscheidungsproblem, if you remember. And because of that, these early interpretations of computation, they were very much related to this kind of logicist paradigm. And then, if you remember, I identified 2 main interpretations. One was about control and automation with cybernetics, with Wiener. And another one was about computation and grammars, so kind of language through computation. And this was with Chomsky. So interesting thing was that as I was doing my research on these research-driven approaches to modeling that I'm going to show you today, for me it was very astonishing to find out that the researchers who did this, they really approached modeling according to these 2 lines. So by these attitudes toward what computation is good for, that came from von Neumann, Wiener, Chomsky, and Lindenmayer. So when you look historically, a big majority of these research-driven computational models in architecture in the last 50 years, they always subscribe to this kind of ideological positions from the last slide. So when I was thinking on how to best categorize these computational models in architecture for the purpose of my work, what I realized that actually I decided to classify them by their kind of ideological influences. So because of that, I have identified legacies of artificial intelligence-based models on the left. Then we have rule-based models in the middle, which are within the tradition of these axiomatic systems and transformational grammars. And on the right, you have control-based models within the tradition of cybernetics and systems theory. And I also provided a more kind of detailed categorization, which you see at the bottom. For example, within these rule-based models in the middle, you have recursive or grammatical models. And then on the other side, within control-based models, you have adaptive models. Then if you go the next step, within the rules-based models, you have these emergent or cellular models. And within the control-based paradigm, you have parametric models. And then finally, within this rule-based tradition, you have logical models. And within the control-based tradition, you have generative models. I will show you why they did it like this. So what I did in my PhD is I described their principles and mathematics that they are based on. And really non-surprisingly, all of these models always embrace the mathematics of their master models. So they always take their mathematics from their master models and adapt it to a current scenario. And even more interestingly, all of these models, in my view, they conceptually follow this logicist tradition of modeling, which I showed you before with formal systems and kind of logic-based approaches, not algebraic. So I will start with the left side, with these AI-based models first. And this kind of computational models are influenced by this early research into artificial intelligence. But before we go there, I would like to give you some background on artificial intelligence. And when computers became reality in the 50s, so what people soon started noticing is that you have a kind of, if you give a computer an appropriate set of instructions, then these digital computers could perform calculations almost infinitely faster than any human can do it. And then it is not difficult to imagine what kind of anxiety this brought to kind of general public. And researchers started questioning whether these machines could be programmed, for example, to think on their own. And of course, this became a great inspiration for science fiction. And in his 1950s paper, Computing Machinery and Intelligence, Alan Turing said, well, this question, whether machines can think or not, it's not a good question to ask. So he suggested we should ask something else. He said, we should ask instead, how well can they perform in so-called imitation game? Maybe you watched the movie, maybe not. An imitation game was a setup in which you have a computer and a human, and they are separated from each other, so they are not aware who is talking to whom, who is on the other side of communication, and they are put into conversation. Yeah? And then this question emerged, which is called a Turing test, and the question is whether computer can be programmed such that it would be so that you are not able to distinguish whether you are talking to a human or a machine. So if you are not able to distinguish, then computer has passed Turing test. And this is a better question than to ask, can they be programmed to think of their own? Because if you cannot distinguish, then it's not relevant. And then a decade later, 1962, Marshall McLuhan wrote a book called Gutenberg Galaxy. You have probably heard it. It was an iconic book. And he coined a term called global village. And he used this term to describe kind of this immediacy of the world that is kind of brought together the whole mankind by communication technologies. And it seemed like society was kind of a gigantic electronic brain or a computer. So I quote him. So he said, but certainly the electromagnetic discoveries have recreated the simultaneous field in all human affairs so that the human family now exists under conditions of a global village. So it's already 1962. And then one of the earlier researchers in the AI and one of the inventors of these artificial neural networks, Marvin Minsky on the right, he defined artificial intelligence as the science of making machines do things that would require intelligence if they were done by men. And then in the conclusion of his 1965 paper, he kind of describes what he expects of future intelligent machines. So I quote him, he says, "When intelligent machines are constructed, we should not be surprised to find them as confused and as stubborn as are men in their convictions about mind matter, consciousness, free will, and the like." So very high hope that this is going to be achieved very quickly, and very naturalized idea of what machine intelligence is. So this is 60s. And one of the earliest examples of computational models that follow this tradition was Ivan Sutherland's Sketchpad. And as you remember, Sketchpad was one of the early examples of computer drawing. But Sutherland's expectations went kind of further than that. He actually wanted his program to understand what are you trying to draw. So if you draw something which looks like a square, but not exactly, the program would kind of make it into a perfect square. And on the right side, you have his prototype for the head-mounted display, which today looks like things you see in gaming industry with these VR headsets. And this was made around the same time as Sketchpad, so very early. And now let's see how this started emerging with architecture. So one important figure in this group was Greek-American architect. His name was Nikola Negroponte. And in 1970, he wrote a book called The Architecture Machine. And then he made an assumption that the future of design is going to be a collaboration between a human designer and a fully conscious, intelligent computers. So his strong belief was that very soon we will have intelligence computers, and we will allow for a kind of evolutionary design process, and then in this mutual process, you have a mutual training, resilience, and growth between computer and a machine. And then he made a kind of distinction between what is a kind of computerized architectural design with these drawing systems, and on the other side he said we have computer aided design, which was about this communication between humans and machines. So for him, in this computer aided design, the goal was that machine kind of learns how to adapt to the designer and to his taste, and also at the same time machine learns some kind of objective truths about the world. And then a few years later, in his book Soft Architecture Machines, then Negroponte introduced into his work this cybernetic idea of feedback loops. So this is now very interesting to observe. So his interpretation of cybernetics led him to completely change his idea of design. So what he decided to do is completely eradicate architects from the design process. So we do not need architects. He says design should be a dialogue between the user and his intelligent house. So you practically talk to a house which adapts itself. And then he described this idea as a kind of responsive architecture. And it was a responsive architecture, as he says, within an intelligent, detached, self-sufficient, sustainable, fully controlled, fully regulated environment. So this is 75. Yeah, so. And he illustrated this idea with a project called Seek. This is the image on the right. Seek is the project from 1970. So you have one huge plexiglass box, and inside you have gerbils. These are small animals, look like rats, family of rats. And there is a number of smaller wooden boxes, and there is a computer-controlled robotic hand above. And this hand regulates the environment. And then, of course, gerbils will constantly move the boxes, and machine was kind of, the idea was that machine will assist them to succeed in doing what they need to do. And yeah, so I will quote him. Its purpose was to show how a machine handled a mismatch between its model of the world and the real world, in this case 502-inch metal-plated cubes. The mismatch was created by a colony of gerbils whose activity constantly disturbed the strictly rectilinear arrangement called by for the machine's model. People usually love this idea very much, even though I'm not sure why, but what usually they do not mention is that most of these poor animals died in this responsive environment. And this is how successful his idea of completely intelligent, detached, self-sufficient, sustainable, fully controlled, and fully regulated environment was. So not very successful for these gerbils. And so his projects were kind of ideological ideas about artificial intelligence, but of course there were some more practical methods, and one of these is called case-based reasoning, or CBR. And it had an assumption that all designs are kind of similar because their design requirements are similar. So because you ask similar things from houses, on that behalf, houses should be similar, for example. So according to this approach, if you need to solve a certain problem, you should not be starting from scratch. You should instead be looking of how similar problems have been solved before, according, of course, to their requirements. So what this system needed to have is a kind of large database of cases. And today, in this age of big data and machine learning, this is really not a problem. But at that time, this was really a big bottleneck. So no internet, so you cannot use, you could not have a kind of exchange platform. And also machine learning was not very successful. So these kind of rules were defined logically. If this happens, then that. But as some researchers say, this didn't really bring any new solutions to architecture. And now, let's look at kind of another category of models, and I call them rule-based models. And they follow this tradition of these transformational grammars of Chomsky and these axiomatic systems. And we can define rule-based models as models whose modeling method is based on the application of rules that evolve the design object. And these models always have a kind of two-level structure from which we can consider the model. So design methods based on rules were among the first ones to be employed in computational design research. And unlike parametric models that you have in software, these kind of models do not have really software that you can install and then play with it. It was usually research. And according to how you implement these rules that guide the design, you can differentiate between a minimum of three approaches to kind of rule-based design. And I define them as recursive or grammatical design models on the left, then kind of emergent or cellular design models in the middle, and logical design models. So now I'll try to explain what it is about and give you a lot of examples. So we define these kind of recursive or grammatical design models as models where this design method really mimics the mechanics of this Turing machine or one of its grammatical derivatives, such as Chomsky's grammars. And they're very much influenced by the large spectrum of these production systems, like we saw with formal system that we made an example on the board. And the main mode of operation of these models is the idea of kind of sequential transformation of geometric entities into new ones. So when we did this formal system, MYU system on the board, I showed you how you can transform strings from one into another by following the rules. Here, what you do is you have rules, and you have a starting geometry, and then you create theorems, which are kind of geometrical entities, not strings, but geometries. So what is different from these Hilbert's ideas is that Hilbert's ideas were designed towards proving a consistency of a formal system, if you remember, or to prove, for example, that prove a theorem. However, here, there is no proof. What you do is simply produce, by rules, a certain geometry. So it's kind of syntactic approach to modeling. And so these systems, they always stratify this design process in two levels. So these two levels are grammar, so elementary propositions, rules, and axioms. And second level is geometry. And this is kind of the rendering of this combinatory potential of these rules. And the promise of this method was that you can really efficiently produce a lot of different geometries from a very, very small number of conditions. So small number of conditions, small amount of rules, but when you combine them together, you get a kind of huge design space. And if you remember this slide from before, this is Aristide Lindenmayer, and the book was Algorithmic Beauty of Plans. And I told you that he kind of influenced architectural modeling with his grammatical approach to growth. But now I can show you where this went through in architecture. So this Lindermeyer's research kind of indicated a path where you can generate forms by using grammars. And this was 1971. George Stinney, American design and computational theorist, he developed this idea further and introduced a system that can be used to manipulate these 2D and 3D shapes, and he named his approach shape grammars. And similar to Chomsky, his intention is to kind of define the complexity of language by means of simple rules, but Stinney says, I'm going to do the same, not with language, but with painting and sculpture. So this is what his title says. The title was Shape Grammars and the Generative Specification of Painting and Sculpture. Yeah? And then in the appendix of the paper, he gave some examples of how can you use this method, and you can see it on the right image. So he submitted his artworks in 2D and 3D, as you can see, but problem is he also continues this legacy of Chomsky by completely ignoring mathematical basis of this procedure, which we saw with Hilbert. So he purely concentrates on this mechanics of transformation of shapes. And this also follows this Chomskyan tradition of how to define a language, and that language for him is simply a set consisting of all possible valid sentences. So for Chomsky, then language is a kind of collection of grammatical instances. So what is ungrammatical is not language. So it's kind of clear separation what is language and what is not. For example, poetry would be in trouble there. And then Stinney and Mitchell simply did the same gesture, but instead of saying language is a set of all possible valid sentences, they would say style is a set of all possible valid architectural expressions. So you have rules that produce a certain expression of geometry, and you say, if this is a valid sentence, valid geometry, then it has a style. So if you could find the geometric rules of a certain style, then every sentence you produce, every instance you produce, by following the same rules, would be kind of a representative of that style. So, and one of the first examples of shape grammars in architecture was this called palladium grammar by Stinney and Mitchell. So this is 1978. So they created a parametric shape grammar to generate floor plans of villas in Palladian style. So they tried to extract what are the rules that Palladio would use. And this is an example of Villa Malcontenta. You can find it in the literature. And for example, another prominent example is 1981, Koenig and Eisenberg. And they used the same system to generate variations of models of Frank Lloyd Wright's prairie-style houses, as you can see here. Another problem that computational architects were facing, and that one of the kind of historical holy grails of computer-aided architectural design, was to kind of generate floor plans automatically. And the problem was that if you make it kind of from this grammatical approach, you get very arbitrary floor plans. So they could not constrain them in any way, because everything was just kind of like Lego bricks. Not like Lego bricks, but kind of expanding on one side, on another side, and just growing. And this is when they start kind of exploring this idea of space allocation. And the idea is that you try to optimize how space is allocated so that space is kind of well packed in a certain boundary. So you can say how many spaces you have, and they will be packed to kind of minimize communications between them and to use the least space and stuff like that. But this was kind of combinatoric based approach, and it was only be able to deal with the simplest arrangements because of something called combinatorial explosion. So the more requirements you have from the system, it becomes exponentially more difficult to find a solution, and at one point it's just impossible to do it like this. And one of the kind of successful and recent implementations of shape grammars in architecture is the work of Müller, Wonka, Hegla, Ulma, and Van Gogh at ETH. And in 2006, they created a sequential shape grammar for the procedural modeling in computer graphics. And they called it CGA Shape. And their system of grammar has 3 levels, just like Chomsky, and they are, number 1, crude volumetric model or a mass model. Second one is called structure of the facade, and third one is called details for windows, doors, and ornaments. Sounds kind of silly when you think about it. But their model was not meant to do architectural design, but rather if you want to kind of simulate what cities looks like or what architecture looks like. And this was most notably meant for game designers and movie kind of special effects designers. And in order to show how well suited this method is for modeling of buildings, they kind of say how they wrote how they compare it to Lindenmeyer's L systems. This was the slide with plants and trees. So they say, we also use a large set of shape rules not existing in L systems. Furthermore, the rules governing a biological system do not directly relate to the modeling of buildings. We found that a direct application of L systems to architecture overemphasizes the idea of growth, a concept that is often counterproductive for the procedural modeling of buildings. So it's kind of still within this grammatic idea of grammars, but kind of abandons the idea of growth. And what was interesting with this model is that only a few years later, after they introduced it, this evolved into a kind of most powerful procedural city generator that you can find. It's called the City Engine. And the authors were very proud how you can kind of program a fully detailed model of a 1 million inhabitant city in a few seconds. And also we had at the chair experience with students making this, and it was not unusual to have a student learn with no background in programming to learn how to do these things, of course not on this level of detail, in 1 semester. So just to show you how powerful this can seem to be if you try to convince someone that cities are geometry. Then it's very easy. In 1 semester you learn to make a geometry of a whole city, and you can be selling that in China in competition or whatever. So this is when you try to argue geometrically today, which I consider very, very problematic, and computationally. And then another approach to shape grammars is called subdivision surfaces. And this is simply exploring the idea of kind of sequentially subdividing larger geometric shapes into smaller geometric shapes. And this is also an example of students' work on subdividing a square. And yeah, in various generations, according to the position of the mouse and whatever else, this square will be subdivided into different triangles on different levels. And if you're interested in references to kind of subdivision and self-similarity, then of course you should be looking at fractals, and then check out a book of Benoit Mandelbrot in the 80s, The Fractal Geometry of Nature, for example. Now we are going more recent. Another example of subdivision surfaces from ETH Zurich, actually from the chair of CAAD. This is Michael Hansmeyer's work from 2010. So he worked on subdivision surfaces, but also kind of improved it. He added parametric control to these parameters of subdivision. And also he integrated search algorithms to the model so that you can kind of search for interesting, kind of save the interesting processes or outcomes. And he called this approach mesh grammars. And in 2010, you might have seen it, he finished a project called Subdivided Columns, a new order. And he designed and produced a kind of series of extraordinarily complex procedural columns. And he fabricated them in a large number of 1 millimeter thick slices of cardboard. And in 2013, he was joined by Benjamin Dillerberger, who has a chair here at the Institute. They worked on a larger project. I don't know if you see anything. Is there a... So they applied this model, but for a different purpose. They wanted to create a kind of larger spatial structure, and the result was called a digital grotesque. It was kind of advertised as first completely 3D printed room, and it had a kind of so far unseen level of details. You probably know it. Do you know this project? Yeah. This is 2018, latest work of Michael Hansmeier in an even larger scale. This is Grotto set design for Mozart's opera, the Zauberflöte, and currently is playing in Brussels. You can see videos on YouTube, or sometimes even tune in to look at the performance. But yeah, you have an idea of what subdivision is about and how can it be used in architecture. Now, let's look at another variation of these kind of rule-based models, and I named them emergent or cellular design models. And they're not about a single object, they're about a population of objects. So what they are interested in, what they emphasize, is this interaction between a large number of smaller entities, and when they interact, this results in a larger pattern, and this larger pattern has a kind of global structure. So if you think of, for example, ants, that on the level of when you look a single ant, you can see that it does some things. But when you see 1 million of them, then you observe a kind of larger structure, which kind of, you ask yourself how these two levels are connected. Of course, this is now not nature, this is algorithmic. But it's kind of mimicking nature in certain regards. So these agents that you program, they follow very simple rules of interaction among the cells and also with the environment. And this is the first level. And the second level is called emergent phenomena. You might have heard of it. And emergent phenomena are usually seen as a kind of geometric rendering of this interaction. So what is the result on a global scale? But if you look at the background, this kind of approach continues this tradition of von Neumann's research into cellular automata and Turing's work on morphogenesis. And this method is also complemented with search and optimization methods, and you will see one of them most prominent, evolutionary programming. But now let's see what this morphogenesis is. Again, we're back to Turing, but now 1952, Turing wrote a paper called Chemical Basis of Morphogenesis, and he slowly kind of started changing his approach towards computation. And then from this linear description of his Turing machine, which has a kind of infinite tape and everything happens on this line, he turned to a kind of nonlinear theory with an idea that he wants to show how complex biological processes we can model them computationally. Yeah, his focus was so-called morphogenesis and how we can model it, or genesis of form. He said, it is suggested that a system of chemical substances called morphogens, reacting together and diffusing through a tissue, is adequate to account for the main phenomena of morphogenesis. So as you can see on the image, his model of morphogenesis is described by a set of differential equations. And then when you simulate such equations on a computer, this led to the development of algorithms called reaction diffusion systems, and they're often exploited in design today. You will see them, you will immediately recognize what this is about, with the purpose of kind of mimicking natural looking processes. And let me show you how they look like. So this is a simulation of a reaction diffusion system. So it models this interaction between different chemical substances in a certain environment and what happens when their concentration changes over time. So you do not define anything geometrically, you define only how they interact. And the results of that are kind of highly unpredictable and very much remind on kind of patterns that you can observe in nature. For example, animal skin patterns like zebras and leopards and stuff like that. Yeah. So to show how is this used today, let's look at one of these videos made by Nervous System for the sports manufacturer New Balance. So here what they do is they analyze runners and they analyze the distribution of pressure on a sole, which happens when you run. So you run and certain areas of the sole get more pressure than the others, yeah? So then they use reaction diffusion algorithms and define concentration of chemicals such that these patterns will get more dense on the areas which are exposed to more pressure, and less dense where there is no such a big need for pressure. Nervous system, you can Google them, you will see they also produce kind of lamps and furniture, which also reminds of these processes, or you can design the jewelry, which is kind of, you can self-generate it in your web browser and stuff like that. So this is what it's based on. And one of the major topics within this field, it's called cellular automata. And this follows this research tradition of John von Neumann that I mentioned earlier. And the general idea was kind of to understand how this complex behavior can emerge from simple rules. And here I will quote John Fraser when he talks about what are these models about. So he said, a cellular automaton consists of a regular array of cells in 1, 2, 3, or more dimensions. Each cell can have at least 2 states. In the simplest automata, these might be 0 or 1, true or false, black or white, alive or dead. But in more complex automata, more states are possible. Each cell is said to have neighbors, which are cells with some specified spatial relationship. In the simplest 2-dimensional grid of squares, a cell might be defined as having 4 edge neighbors, or 8, including those on the diagonal. And one of the most prominent examples of this cellular automata is so-called game of life, developed by John Conway in the 60s. And it's also a great example to discuss how computational architects often naturalize these algorithms. And game of life appears to kind of simulate lifelike behavior, and it is really described as if this was really true. So researchers observed some emerging patterns of the game, and they named them in a very naturalized language. For example, they describe some cells as being alive, dead, lonely, and then you have larger patterns that emerge. They gave them names such as pulsar, toad, glider, spaceship. So it's kind of, at one moment in time, it was very symptomatic that we try to naturalize these things, that we see algorithms which are pure rules and try to see something natural in them. And this, of course, might not be a big deal if you make games, but if you try to, for example, model biology based on these principles, then you might get in trouble. And this is one of the points that I would like to make here. Often architects and computer programmers ignore the historicity of these paradigms, and this ignorance sometimes gets even worse and more amplified with more generations of kind of followers. So we have seen this with Chomsky. So Chomsky, when he introduced his grammars, first thing he did, he dismissed probability of language models. And as you will see later, quantum theory is completely based on probabilities. But first thing he did, he said no. Then I introduced you with Stinney's shape grammars. What he did is he followed Chomsky and then further limited this grammatical approach. So he started using rules to make geometry and completely forgetting about Hilbert. And sometimes this ignorance goes into complete hostility towards mathematics. As we can see with Coates, he was also a follower of Chomsky and Stinney, so third generation. So he says, cellular automaton model seems to be more natural and considerably simpler. However, the traditional mathematical approach still has greater academic prestige and is used in preference to the simpler explanation. Yet another example of the dead hand of Victorian mathematics at work. So with these simpler rules and emergent phenomena, people get obsessed with the simplicity and says, yes, this is it. It's simple. We do not have to care about the historicity. We do not have to care about everything that happened in this line of reasoning. It works. Just use it. That's it. That's nature. And yeah, this is something that you should be careful about, not forget. Another interesting concept utilized in design was the idea of a swarm system. And this was inspired by Craig Reynolds' flocking algorithm from 1986. So he had built a swarm system, and it consisted of agents called boids or birds in New York accent. And these birds fly together and simulate this phenomena of bird flocking. And how this works is quite interesting from a certain standpoint, because there are only 3 rules that you need to implement here. And all 3 rules you give to a single bird. You do not define their behavior, you just define behavior of a single boid. So, let me tell you what these are. Each bird should steer to avoid the crowd. Second one, each boid should align towards the average heading. And third one, each bird should move towards the center of the mass of its flockmates. And as you can imagine, with mathematics, it's very easy to calculate the center of all of their geometrical positions and all of these things. And once you start simulating that, what emerges is kind of organic movement, which looks like flocking behavior of the birds. And then what people say is, yes, this is how birds fly. That's it. You can describe it with an algorithm. We do not need science. That's it. Because it looks like that. This is, again, pre-19th century idea. Because if it looks like that, it must be that. What else? Yeah? But nevertheless, these instances were used also for design, especially in UK, most notably Design Research Laboratory of the Architectural Association School of Architecture. And another important class of models in this field are called evolutionary algorithms or genetic algorithms. And we can think of them as a kind of search and optimization technique, which is modeled upon Darwin's idea of natural selection, which is also very interesting. So every object now, we can see it from 2 levels. Again, it's of course, it's about collections of objects, not about a single object. So you have a level of a genotype or genetic code and a phenotype, which is kind of the candidate solutions for its species. And then when you have a population that has a particular property, or a population of objects that have a particular group of properties, and you say these properties are desirable in this population, this is what I want to have, this is what I want to produce, then you can use something called a fitness function to optimize so that these properties are seen more. Yeah? And this is done in time intervals called generations. So it kind of mimics the process, natural processes, which are described by Darwin. And then you have 3 operators which do that, which are involved into this: selection, or like natural selection, crossover, and mutation. Yeah. And one of the most prominent researchers which was thinking about how to apply this in architecture was John Fraser. And he described it as a kind of form of artificial life where highly naturalized notions of environment and rules were inherited from cellular automata and translated to the representation of genetic code so that they can be evolved with the use of genetic algorithms. So, to make it simpler, his intention was to shift this notion of architectural language that we agree upon from blueprints that we use to a kind of genetic language of architecture, where architectural concept would be described as a genetic code in a similar way that Darwin describes life. And I will give you an example. 1994, prominent examples from Carl Sims called evolved virtual creatures. And these are algorithms that use this genetic programming to optimize certain features of the agents. For example, here, an agent needs to learn how to move efficiently. So it starts moving randomly. You implement some kind of notion of physics and kinematics or dynamics, and then the next generation of agents, if it moves more efficiently than the previous one, then it is allowed to reproduce and transfer its genotype to the next generation. And if not, then it dies. Yeah? And instead of those dying species, you introduce mutations and hope that with mutations, there's a chance that one of them, which mutates, will be more efficient than the previous generations. If it is more efficient, you keep it. If it's not, you discard it and have more mutations. And then in generations, you get things which are more and more optimized toward a certain criteria. Yeah? So this was the idea. It did not go very far in architecture, but in 1995, theoretically, it kind of did. Fraser wrote a book called An Evolutionary Architecture, and he described a theoretical model of how architecture could be based on this emergent phenomena. And this approach claimed to kind of be based on nature as the generating force for architectural forms. So he said, yeah, it's not me who is who is making rules about how this should evolve. It's nature. So this is very interesting, giving responsibility to nature within computers. But for me, it really fell short to define how is this really nature, how the nature is the same as mimicry. This is, again, being obsessed with visual, trusting your senses. Yeah? And in order to be more close to nature and to distance themselves from these rules, so this is another interesting thing. Again, forget mathematics as far as you can. So forget that these are Hilbert's formal systems and proof for consistency. Forget about it. Because we are natural. And therefore, they try to kind of distance themselves from computational approaches like these shape grammars and these Mitchell's approaches. So they simply says, we are interested in this Turing's legacy of morphogenesis, and then we will enhance it with these genetic programming methods and genetic algorithms, because like that we can model biological evolutionary processes. And of course, for Fraser, who wrote this, it was important for him to be in tune with kind of prominent computational paradigms of the time. So in the postscript of his book, Tim Yachna wrote how he considers the relation between this evolutionary architecture to cybernetics. So he said, an evolutionary architecture will exhibit metabolism. It will enjoy a thermodynamically open relationship with the environment in both a metabolic and a socioeconomic sense. It will maintain stability with the environment by negative feedback interactions and promote evolution in its employment of positive feedback. It will conserve information while using the processes of autopoiesis, autocatalysis, and emergent behavior to generate new forms and structures. However, Fraser is kind of trying to avoid the work of Wiener, probably because he saw what it did to Negroponte. He also says, yeah, Negroponte was kind of unreasonable with his expectation of artificial intelligence, which did not really deliver any answers. So instead of being visionary here, Fraser is kind of pragmatic. And the last group of models that we will define here are the logic-based design models. And I define them as the models whose utilize formal reasoning, so formal rule following and reasoning as a principal mode of design. And they do not deal with geometry directly, but they codify the application of design statements or decisions in a kind of logical form. So they create rules of design, so to say. And the first example of logic-based models we can create to our Christopher Alexander in his book Notes on the Synthesis of Form from 1964. And for him, interestingly enough, the ultimate object of design is form. And the difficulty with architectural form is how you connect form with design needs. So this is how he defines the main problem of his book. Yeah? He says there is no way to create a mapping which would allow us to evaluate the form according to the needs that we want from it. Yeah? And instead of concentrating on the operation of various systems as subsystems that are generators of form, he says, he introduced an idea of a pattern as a kind of independent, abstracted unit which encapsulates a certain bundle of relationships which resolve a small or interacting and conflicting, small systems of interacting and conflicting forces, and it's independent of all other forces and of all other possible diagrams. So he kind of tries to find smaller units which have certain connection to each other in a way of kind of logical system, how one goes through the other, how one is followed by the other, and express a network of patterns which you can use to design. Yeah? And in 1977, he went further with this, and he wrote a book called The Pattern Language, and he collected 253 patterns for the design of buildings and cities. And he said, if you correctly follow these patterns that I wrote, this should guide and constrain the design. Yeah? So then his design was kind of explained as an abstract language, and this organization of patterns reflected these notions of vocabulary, syntax, and grammar. And even though this is a kind of very abstract idea when you think about design, the actual implementation that he did there simply consisted of following the rules that he made for you, yeah, within a logical network. So similar to how Chomsky defines grammar. You have a certain case of axioms and certain number of rules, and as long as you follow them, you get a good design. It is the same here. As long as you follow the patterns and combine them in a way, you get good architecture. But on the other side, the person who invented the system is him. So why should you trust him that he knows the rules about how you should do architecture? Yeah. So instead of going more, I mean, this was a long time ago. Today, what someone would try to do is make more abstract rules about design, not concrete rules. Yeah, like he did. And let me give you some examples. One is 1990. William Mitchell, I show you, he was working on these palladium shape grammars. He wrote the book, The Logic of Architecture, and then he explained his method of design there. So his main concern for him was to find a language which is suited for computer-aided architectural design, and then how you can create such a language by combining computation and logic. So how he did it? He made a distinction between form and requirements in the same way as Alexander did, but he turned it into kind of very pragmatic perspective based on Chomsky's approach, so that you have a typical grammatical system with axioms, with rules, and with theorems, and yeah. So instead of having systems and subsystems like in these patterns, he made it into a kind of transformational grammar. And these constitutions of the generative system, he said, these are design worlds, and these design worlds provide graphic tokens which can be manipulated according to certain grammatical rules. Yeah? So instead of using set theory, like Alexander, he uses first-order predicate calculus. So remember the first class we did with predicate calculus. So for example, in order to define color, length, and material of a Parthenon, he uses the following predicates. So color, and then parentheses, Parthenon X. It means that Parthenon is assigned color, which is represented by the variable x. Parthenon is assigned length, described by the variable y. And Parthenon is described material in the same way, assigned material with the variable z. Or, for example, this is completely the language of logic on the bottom left. How to describe that each column should be fluted. He says for each column, fluted should be its property. So it's a very logical way of describing things. Yeah? So he also gave an example of how, for example, an axiom should look like in this design process. So he said there, a world of wooden blocks, for example, is governed by an axiom that two blocks cannot be in the same place at the same time. Yeah? Not very exciting, but you can find his book in the library. Again, what happens is again this war against mathematics. Algebraic thinking is not really easily coexisting between logicians. As I showed you in the beginning, this the distinction that I made about logicist approaches and algebraist approaches, again, you can see it here, a couple of generations later in a very different field, how this hate towards algebra is manifested. So he says, the trouble with algebras as universes of design possibilities is that they usually contain too much. They tend to contain vast number of possibilities that have no architectural meaning whatsoever, plus possibilities that are meaningful but irrelevant or interesting. So he's kind of afraid of these lots that we have today. His problem with algebra is that it contains everything there is. So for him, this is too much. He needs to find rules which will tell him what is good and what is bad. Today, and I will show you how this works in algebraic approaches, this is not really a problem. But it is a problem for a logician. Yeah? And one more of these kind of systems, from that time, logical systems for design were called expert systems. They are from the 80s. And they capture knowledge in form of kind of design rules. So you take knowledge about design and define it as a type of a rules. If I see this, then I do that. Yeah? And then what they try to do is say, we need to ask experts to give us as many as these rules as possible. And then we need to kind of contain them in a system and put them at disposal for non-experts to use. Yeah? So you cannot really evaluate them in respect to any design problem. Only you can evaluate them whether you are applying the correct rules or not. Yeah? That's why I call them that's why I call them logic-based models. And yeah, in order to go from one case to another, to apply rules, you use something called an inference engine, which is also a logical term. Yeah, you apply rules to the facts in order to reach conclusions. And then the last group of models in this group, within a larger group of rule-based models. Sorry, we were talking about rule-based models so far, but now this is a second generation of models which is more inspired by the cybernetic approach, with which I showed you with Wiener, and I named them control-based design models. And these are the models whose kind of unified system of procedures governs the creation and manipulation of spatial form. Yeah? So it's a unified system of procedures, not a certain rules. And this modeling methods allows you to control this unified system as a whole. So you have a unified system of procedures that you define, top down, and you are able to control this system as a whole. And this is a very strictly top-down modeling paradigm, and it relies on the ideas of control and regulation within a system. And then we can say that these models learned from the tradition of cybernetics. And instead of, unlike these rule-based models that we've seen so far, control-based models mostly rely not on design of rules, but on the design of constraints. Yeah? So according to how these control mechanisms you implement, then you can again start to differentiate between different approaches to control-based design. And I would say that you can definitely distinguish between adaptive models, parametric models, and generative models. So this is my assumption. So let me try to explain what I mean and also show you what kind of models we talk about. So adaptive models, I would say these are models that employ feedback chains and automation. And in my understanding, they directly follow Wiener's cybernetics tradition. So they are based on feedback principle, where you have output of a machine being linked to this input, and then you compare that against some performance measurement. Yeah? And simple examples of adaptation you can find in kind of everyday architecture. And for example, control, regulation, supervision of electrical, mechanical, climatic control equipment. Yeah? And simply what they do is there are certain events. These models register these events and respond to them. And more complex models of this kind, they kind of go a step further than just respond. They kind of anticipate what is going to happen in the future, and then they do it before it happens. So they're called model-based adaptability models. Yeah. As an example, I have a quote from Kalai, who said, similarly, a house equipped with such a model-based adaptability system could optimize household operations, for example, by turning on the water heater an hour before the washer is scheduled to be used, thus ensuring that there is plenty of hot water available by the time it is needed and avoiding wasting energy when hot water is not needed. Of course, in today's world of sustainability, these are super popular to optimize energy usage and all of these things. This is also research from the ETH. Yeah? And now, let's speak about a little bit parametric models. This is what is, again, very popular today. And so what parametric models are not a thing or their own. They always exist within a kind of certain geometrical modeler, within a certain infrastructure, like I showed you before, for example, surface modelers or solid modelers. And what they do is they take the objects of these modelers, for example, points, vertices, edges, curves, surfaces, and volumes, and they describe them and describe their associative relations or constrain one to another, yeah? So then you create a new aggregated parameters which are associating certain things. For example, a relation between two lines. You say that two lines should be perpendicular to each other, yeah? So then you introduce a parameter, parameter x, which must ensure that however you move this line, yeah, here, it should always be perpendicular. Or when you draw a circle, you say that the line I want to draw must be a tangent. So if you try to draw a line like this, it will not allow you. It will say not illegal move. So if you will need to be able to only move the line on a circle. So there's a parameter which describes this relation. And this is what is called constraints, yeah? And in this way, you can create a kind of efficient libraries of these components. And for example, constraints, what you can have as constraints would be to align, for example, points, axes, surfaces, tangency. Yeah. And these relations are always described as kind of algebraic equations. And you need to solve algebraic equation to see what is the limit of a certain parameter. What would be its state where it can exist and where it is invalid, for example. Yeah. So, but I don't want to go into detail. I could now, of course, describe mathematics of that, which would be maybe not even relevant. If you're interested, you can find it out. But let me just tell you about a little bit of history. These, unlike these grammatical models that we've seen before, these were not only research things. They were released as commercial software, and they were kind of designed for a specific profile of users, and they appeared in the 70s and built on top of these solid modelers. And in 1977, French aerospace company Dassault Systems, or Dassault Aviation, started developing a software called CATIA, and this kind of set a standard for all of these parametric modelers at the time, and it's one of the most successful parametric products. And then in 80s and 90s, there were more softwares such as MicroStation, ProEngineer, SolidWorks. But CATIA remained as the kind of most extensive implementation, and the one which was mostly used in architectural modeling. And the American architect Frank Gehry, he was very much interested in power of parametric modelers. He used CATIA version 4 to design and develop his new Guggenheim Museum project in Bilbao in 1997. Yeah? So the idea was that you have a whole future building completely contained in a parametrically defined model. So it's not only geometry, it's also how certain parts in this model are related to each other. So each element has its own place in a kind of global chain of dependencies and constraints. And this allowed to have a great precision in computing the final geometry. And what you can do is that you can send your model directly to the manufacturing plants without actually ever drawing these things. And this kind of also pushed the boundaries of what you can do with architectural geometry, and it kind of pushed the boundaries of what you can build, actually. And there's a video from the SAW systems where Gary kind of conveys his idea of what is the future of architectural modeling, and he said, at one moment, he says, they have built Boeing 777 with no paper. This is what we want, yeah? So what happened is that Gary Technologies and the SAW systems, they started collaborating on a new version of CATIA. And in 1999, they made a software called Digital Project. And this was a kind of fully parametric architectural modeling software. And what it did, it introduced an idea of a model tree to a 3D model. So you can start having kind of simple 2D sketches, and then started evolving from this. You say the first level would be a 2D arc, and then you can extrude it, and then you say it should have certain number of divisions, and on the third division it should start continue flat or whatever. So you kind of evolve it from a simple sketch towards a fully built model. And you can constrain things, for example. Certain line should always be parallel to the ground, or should be always 15 degrees angle to the ground, and stuff like that. And this, of course, also had an influence of architectural theory. And in 2008, Patrick Schumacher, he wrote his Parametricist Manifesto, and he was practically in the book celebrating the efficiency of these new tools and kind of how you can radically economize the architecture made possible by these new tools. And yeah, one more thing here, which you should know about, is parametric models often have this thing called building information modeling. And because of that, sometimes they call these tools BIM software. And I would like to expose to you that this is really not the truth. And I want to show you what BIM really is about and how it came about. So BIM was conceived very early, in parallel with the first CAD software in 1970s, at the very beginning of computer-aided architectural modeling. So one side, you have this geometrical route, where you have this CAD software interested in modeling geometry. But on the other side, you had a kind of concern, how do we describe buildings? How do we describe it so that we can support construction industry? How we can say how much, how many things we want to have? How we describe how heavy something is, or what is the area of something, you know? How do you describe quantities, not only geometry? And one of the pioneers of this route was called, I mean, he's still alive, Charles Eastman, and he wrote a paper in 1974. It's called An Outline of the Building Description System. And his main concern was not geometry, but cost of design, construction, and building operation. And he said that he was complaining that the software at the time was too much relied on graphical descriptions containing drawings. And he made a prototype, kind of theoretical prototype. What he did is that these elements of the drawing can be grouped together, and then the groups can be nested in a hierarchical system. So you would not only have a line or a kind of four, you would not have just two lines representing a wall, or having 6 faces describing a column. He would say, yeah, what you need to do is you need to group. You need to, yes, this is 6 faces, but what I'm interested in is defining this as a kind of element. And I want to say, this is a column. So I need to make a grouping of this and name it somehow, yeah? And then see how many of these kind of things we have. And what you would do then is kind of make a hierarchy of everything that is contained in a geometry and name it. And then you name each of these elements, then you measure them. For example, you would measure the area of this, and then you describe it with metadata. Yeah? So it's not anymore that you have only geometrical description, but with every of these things, you would associate a table, which is called a metadata. And then you would say here name, or whatever. You can see it on the image. Body, face, edge, vertex, you know, and then you can, you see it on the screen. And he believed that such kind of semantic ontology would allow much more appropriate description for the industry than drawings. So he says this is better for the industry. And when solid modelers came to the scene, then Eastman's approach was really easy and possible to implement because each solid object could be easily measured because it's kind of described topologically. Yeah? And his work also coincided with the development of computer databases. And for example, SQL database language, which was made for querying databases, was introduced the same year as this paper. And with databases in which you can kind of organize these things, they made this task of storing these descriptions very easy. But what was problematic now was how do we describe this ontology? How do we make these descriptions? How do we agree of what is a wall, what is a column, what is a light fixture? You know, how do we agree upon these names? How do we name them? How should we group them? How should we characterize them so that each one of us, when we have a model, we can kind of immediately recognize what it is about? And from that, it was something was born. It was called Industry Foundation Classes Initiative. This was a kind of initiative started by Autodesk in 1994. And this was kind of industry-developed product data model for, it's called Industry-Developed Product Data Model for the Design and Full Life Cycle of Buildings. Yeah? And this is kind of made to be a format, common format for all the BIM softwares that integrate this BIM. So to know better now what BIM is not a modeling system. BIM is a semantic ontology which can be attached to any modeling software, any modeling implementation, as long as this software allows its elements to be measured and described. So as long as you can group things and name them and have kind of metadata, this allows to have BIM. So it's not about modeling. It doesn't matter if software is parametric or not. It does not change the implementation of BIM. It just makes it more or less efficient. And of course, in the 2000s, all major packages used for design of buildings became parametric, and all of them started using BIM. And of course, one of the most popular examples on the simplicity side was Autodesk Revit in 2000. And if you want more advanced parametric BIM modelers, then you would look at generative components from 2003. And the last type of model we have here is called generative models. And the name suggests that this might have something to do with Chomsky's generative grammars, but it's a different kind of modeling. And if you have 3D Studio Max or software like that, then you will know what this is about. This is a kind of history-based modeling. So what you have is you construct an object by applying stacks of transformations. You have a starting geometry, and then you apply a modifier 1, which extrudes things, modifier 2, which kind of expands it, modifier 3, which tapers it, and stuff like that. So then you have a stacking of transformations, and this is stored as the object. So the object is the starting geometry plus all the transformations together. And because of these protocols, they're always compatible. You always know what is the result going to be like. Then you can kind of build your own system of design with this. Yeah? And there is no rules how to do these transformations. You can simply freely do them one after another. Yeah? And so if parametric tools were always related to, for example, solid modelers, these kind of tools are always related with surface modeling software. For example, 3D Studio Max in 1990s, or Cinema 4D, or Maya. These are kind of the examples. And yeah, if I show you, as I showed you before, this focus of 3D animation and computer graphics was not in the modeling, but of kind of trying to provide a comprehensive integration of solutions that simulate physical space. And over the time, most of these software started including kind of kinematics, skeletons, dynamics, particle systems. And all of these kind of dynamical aspects of these tools started inspiring people, also in theory, especially American architect Greg Lynn. And he defined his own architectural theory and program. And in his 1999 book, Animate Form, he invited architects to kind of abandon this safety of static Cartesian organizations and embrace this dynamism of these models by inviting these ideas of force and motion into the environment. And this force and motion was actually inspired by these softwares which were used for 3D animation. And he says, virtual movement of such forces allows form to occupy a multiplicity of possible positions continuously with the same form. To embrace his perspective, he offered a very easy solution: simply embrace modern animation software and its topological landscapes. Yeah. So if we look at what was presented so far, we can distinguish between two different contexts in which computational models have developed. So on one side, we have computational models that are made within a commercial software like AutoCAD, Maya, CATIA. And on the other side, you have these more research-driven models which are not part of any software, which were all part of scientific papers. And in the beginning of 21st century, this stability was no longer there because of internet. So how it all started, it started with the kind of extension of existing tools with so-called scripting. And scripting as the kind of ability to take charge of modeling by programming, by using code within a software. This was first introduced in AutoLisp in 1980s, so this was AutoCAD. And in 1997, then Autodesk introduces MaxScript for 3D Studio Max, and in 1998, Alias Systems Corporation introduced MEL scripting for Maya software. And today, all of these softwares integrate some kind of scripting abilities. Yeah. And this new possibility that you can kind of collaborate independent of location, because you have internet, this spawned a movement called open source software movement, or open source development communities, which were kind of brought together by their interests. So you are connecting with people who are interested in the same things. But also you can make products with them on the internet if you can share code. And such collaborative developments, you have spawned software like Blender or FreeCAD, and also modeling libraries for programming languages, for example, OpenCascade in 1999 or ToxiLibs in 2010. And finally, you started having new programming languages and their dialects used for kind of graphic and spatial design, and then you have there, for example, processing in 2001, Open Frameworks 2005, Grasshopper 2007, Cinder 2010, and also they were extended to the web, for example, Processing.js 2008 or WebGL 2011. And because of internet, not only that you had kind of easy access to these tools, but you can also collaboratively explore, create and aggregate their technical documentation. And very soon, as you know, you started having many tutorials available to anyone who is interested to learn. But the biggest difficulty with these developments that users were required to actually know how to program computers, whether to write a code or manipulate the code that was already given in the libraries. Yeah? And what happens is that all of a sudden, all these computational models that I have shown you today, also with their infrastructure in geometric modeling and computer graphics, everything became available online, encapsulated in code, documented, discussed, and taught in schools. And of course, one of the most prominent places, one of them was, of course, AA in London. Since computing was kind of considered to be advanced topic, it didn't go directly to, for example, bachelor programs or master programs, but went into kind of emerged the rise of postgraduate programs like Master 2, and this was kind of aimed to introduce computer technology to architects, practically for teach them how to program. And there was in 1997, AA created a new graduate program called Design Research Lab. But it's interesting to know that this was also already existing in Switzerland. A similar postgraduate program which had an interest in exploring relation between computers architecture in the virtual. This was established in Switzerland in 1992 by Professor Gerhard Schmidt. But then it was kind of redefined in 2000 when Ludger Hoverstadt replaced Schmidt on that position of the professorship for the chair of computer-aided architectural design. So what Hoverstadt did was took this research, which was into virtual relation between architecture and computers. He introduced his research under a different slogan, which was kind of back to reality. So explore the kind of pragmatic real-world relation between architecture and computation. And then after 10 years of research, there was over 100 experiments made at the chair. And this is documented in the book called Beyond the Grid in 2009. And yeah, this long relationship, this long introduction that I made here to put light on this elusive relationship between architecture and digital computers, this helps to kind of understand what kind of computational paradigms are involved in architectural modeling. And sadly today what we can observe is that most of the models we use today in architectural practice do not really involve computation unless when we think about infrastructures. And majority of those that are computational today, they follow these traditions of early research in artificial intelligence, then this top-down control paradigm of cybernetics, or this bottom-up rule-based paradigm of formal systems. And then what happened is that these paradigms are kind of further developed and hybridized, so everything is combined with everything within these architectural education centers and master programs and research institutes. And this results with kind of formally exciting and sometimes unimaginable artifacts that we saw today. And then with internet, what happens is that this kind of fruits of this collective effort were kind of democratized and kind of started being available to everyone. And then this results with kind of development of new tools and new methods and a kind of new generations of architects which are also programmers. But then I would like to mention a potential risk which comes with this cheerful optimism of of kind of programmable contemporary design tools. So in many tools that we have available and which are programmable, this programming often takes place within already existing model. And the ontology of this model is hidden from the user because it is meant to be simple to use. So this simplicity sometimes can empower a designer to kind of quickly develop something, but the problem is this simplicity also stops you for comprehending the bigger picture. So in this sense, knowing how to program, but without understanding this general abstract nature of models, this can even be counterproductive, in my opinion. And also, what I need to mention is that all of these models simply appropriated the model of space and time from computer graphics without kind of reflecting on the potential impact. And as I told you, creating of this infrastructure often depends on mathematics, for example, differential geometry, topology, calculus. And this can kind of give you a kind of fake sense of mathematical depth to computational modeling in architecture. But mostly why computational modeling in architecture is effective is because we have fast computers. So because of that, from next chapter on, we are finished with what we know, yeah? And we will plunge into unknown territory. So we will try to see an alternative to this. I want to show you that these kind of computational paradigms that you have seen represent only a very small part of spectrum of what is possible and what is used in information technology today. And because of that, what I'm going to show you, it's maybe not even an overstatement to say that all of these computational models in architecture that they really have not advanced much since their early beginnings. We're kind of rotating around the same concept in the last 50 years. And my chair that I'm part of, Chair of Computer-Aided Architectural Design, we have experienced this deadlock very early. And we understand what kind of overarching consequences this has also to architecture and to society. And in 2009, the chair kind of abandoned this route of doing, and we started thinking about what are computers really good for and what computation is all about. So we started kind of, after many experiments, taking a step back and saying, okay, we now see it from a larger perspective, and we see that information technology has went to a completely another side, and also science, but we are still here. How we can change our perspective? Where should we look further, yeah? And this question, what to do next, cannot be answered within these tools that we have seen now, and cannot be answered within this mathematics, and cannot be understood within the idea of the world that this kind of subsumes. So if we want to ask what's next, we need to research into the other side, which I called kind of algebraic perspective to modeling. And this is what we will start from next time. So it will be more conceptual, more complicated, but I will try to explain you where we might be, where we may be productive if we look at, you know. So yeah, that's it for today. And thank you for your patience. And if you have some questions, it would be good to ask. Or if you want me to repeat something, or if you didn't understand some part, you know it. Or you would want me to go slower next time, or... Did you know about all these computational approaches? All the references that I gave you, have you seen them before? No? Did you know about these evolved virtual creatures that learn how to walk and stuff? Yeah. I just tried to give you an overview where it comes from, and yeah. Give you these early examples because many of the examples you will see today are kind of following what I've shown you here conceptually. Yeah. Carl Sims. Yeah. He was not an architect. But you understand the idea, so you use kind of, you try to implement Darwin's idea of natural selection into computation by kind of encoding these principles of selection and mutation and crossover. So you have a generation of things, and you say, what I want for them is to move. So I want to calculate in a certain amount of time how far can they go. And I say if they can go further, this is what I want. If they move only a little, this is what I don't want. So I'm trying to optimize for this one measure, which is distance over time. Yeah. Then you construct them randomly and see some of them will be better than the others. And then you say those who are better, I know that they're better because I can measure their performance. We should keep them, and we should cross over, we should reproduce them, we should mix them among each other. Yeah? And those that are not good, we should discard them. But at the same time, we will involve some of them which are mutated. We will mutate some of them. And then it can happen that if you make a crossover, some of the new ones will be better than the old ones, then these should continue to reproduce, while the ones that are not, we should keep them. And in this way, in each generation, you kind of randomly come to species which are better at doing this one task. But always you need to know what is this criteria that you're optimizing. You cannot optimize everything. It's always better if you have a smaller criteria in mind to optimize. It's a very simple idea, but it's kind of effective. It's also effective optimization strategy for not only for this, but for anything. Because sometimes you cannot solve things analytically. You cannot find an answer. And then you do it randomly. One of the examples of this in architecture, I don't know why I didn't put it, was Herzog-de Meuron Stadium in Beijing, the one which looks like a bird's nest. You know that? So the idea was that they wanted to have the roof, when you look at it from above, is made of straight lines, yeah? Of course, the middle does not have anything. Yeah? Problem was, when they tried to make it by hand, first of all, this is a problem with more unknowns than the number of equations. Therefore, you cannot solve it analytically. There are infinite number of solutions. So analytically, it's not unsolvable. Then designers started drawing lines. And then realized they draw 100 lines, or I don't know, more lines, but problem is they have too big, so parts which are too big to be static, to be good for construction. So it's not good for statics, or too small, so that they are not easy to manufacture. So they needed to have a balance between openings that are too big and too small. And they cannot solve it. The only solution was to draw more and more and see what happens. And they could not able to solve it in months. And then they asked some people from the chair of computer-aided design, architectural design here, and they made a model, which was evolutionary model, in a couple of generations, which was using the same idea of this Carl Sims evolved what was it called? You know, these things that learn how to walk. So they use the same idea to just randomly generate a generation of 100 lines, then measure all the kind of intersections between them, see if they are too small and too big, and reward the solutions which were more optimal than the others. Yeah. So if it has too many of big openings, you discard it. If it has kind of more equal, then keep it. And in a couple of generations, they solved the problem. So they solved the problem within a few days. And this took months before to solve. So some things are simply undrawable. Some things are not solvable by analytic means. And sometimes these examples these models can be used. Something else? Well, if not, then those of you who came around 1, please sign that you have been here. If you came 1 hour later, please don't.